Thank you. And thank you very much to the organizers for letting me give a second talk. So I'll be speaking about the quasi-Einstein equations, mostly in 2 dimensions, but near the end I'll also consider some higher dimensional cases. So the first part of my talk is based on joint work with Maciek, Harry Konduri, and James Luchetti. And the second part contains some work in progress with Maciek. So in the second part, there are still some open problems, and I will get to those. Let me start at the beginning. So the setup is as follows. We have a manifold M of dimension n with a Riemannian metric G and a vector field X satisfying the quasi-Einstein equations. These are these equations which we're solving simultaneously for the metric G and the vector field X. So the equations is Ricci tensor of G is some non-zero constant, which I called 1 over m, times the one-form dual to X tensor itself, minus a bit of the Lie derivative of the metric with respect to X, plus some constant lambda times the metric G. And so there are various reasons to be interested in these equations. They appear in different contexts for different values of this constant m. And I'll mention some of those. So first of all, when m equals 2, this equation is relevant in general relativity, and it is the near horizon equation describing cross-sections of horizons of extremal black hole spacetimes, where the spacetime is a Lorentzian solution to the Einstein equations with cosmological constant lambda. So I talked about this case in detail last week. And here, usually, the manifold M is assumed to be compact. Now, when M is 1 minus the dimension of the manifold, so in 2 dimensions, this would be M equals minus 1, and we take the cosmological constant to be 0, this equation describes Levi-Civita connections that are projectively equivalent to connections with a skew-symmetric Ricci tensor. And I'll come back to this case. And when m is 2 minus n, so here necessarily n is at least 3, this is the value of m for which the equation has some nice conformal properties, and it's related to the Einstein-Waal equation. And also come back to this in the compact setting. And when m is any positive integer and the one-form dual to X is exact, this equation describes warped product Einstein metrics. So if we take m to be our base manifold, and we take a warped product with another manifold of dimension little m, then we can impose the Einstein equations on this warped product metric, and they will imply that m is a quasi-Einstein manifold with the one form given by the gradient of the function doing the warping. And then finally, when the x squared term disappears, which you can formally include as the case m equals infinity, this is the Ricci soliton equation describing self-similar solutions to the Ricci flow. So the outline of my talk is as follows. I'll first consider the 2-dimensional quasi-Einstein equation for general m, but assuming some symmetry. Then I will specialize to the value of m that is related to this projective metrizability problem. In 2 dimensions, it turns out that the relevant equations arise as a symmetry reduction of anti-self-dual Yang-Mills, and this allows us to associate a solution to the Hitchin equations to our problem. And then finally, I'll consider some higher dimensional cases for the value of m that is related to Einstein-Waal structures. So I'll begin with some general remarks. First of all, we could, of course, take the vector field to be identically 0, and then the quasi-Einstein equation reduces to the Einstein equation. And I'm going to refer to solutions obtained in this way as trivial. And then in 2 dimensions, we have the following result. If we have a non-trivial solution on a compact surface, then this surface up to a double cover has to be the sphere. So I proved this in my last talk for, in fact, a more general class of equations. So one way to prove this is to apply the Poincaré-Hopf theorem to this vector field X, which involves showing that X can only have isolated zeros of positive index, which then implies the Euler characteristic has to be positive. And an immediate corollary of this is that there are no non-trivial quasi-Einstein metrics on a compact surface when m and lambda are both non-positive. So this follows by taking the trace of the quasi-Einstein equation and integrating it over the manifold. So here on the right-hand side, if the solution is non-trivial, this first term will have a negative integral, second term integrates to 0, and the third term is also non-positive. However, the left-hand side integrates to 8 pi by the Gauss-Bonnet theorem, so we find a contradiction. And moreover, when m is outside the open interval 0, 2, there is in fact a much stronger result, which is that any solution to this equation on the two-sphere must have a Killing vector. So the proof is, there is a generalization of a proof introduced by Maciek and James Luchetti for m equals 2, where essentially you make an ansatz for the Killing vector using this vector field x, and then you do some integrations by parts to show that this ansatz has to be Killing. So in the following, I will be assuming that our solutions have a Killing vector, but it's important to keep in mind that for almost all m, this assumption of symmetry follows from the compactness assumption. So I come now to the main result of this preprint. So if we have a solution admitting a U1 isometric action such that the one-form dual to x is not closed, then we can in fact completely solve this Quasi-Einstein equation. So locally, there exists some coordinates x and phi adapted to this U1 action, together with a function b, which is the norm squared of the Killing vector, such that the solution takes this form. So this is the metric, and this x will also be completely determined by b, and b contains two arbitrary constants, small b and small c, and moreover, it depends on a hypergeometric function. And also, we have to consider the case m equals -1 separately. So this case is a bit special because this is the case corresponding to this projective metrizability problem. So all of this is a local statement. Now there's also a global statement, which is the following. If we take the constant b to be 0 and choose c as in this table, then in fact this local solution extends to a smooth solution defined on the two-sphere. And conversely, every solution on the two-sphere that has a Killing vector arises in this way. So note that when lambda and m are both non-positive, there is in fact no c such that the solution extends, which is consistent with what I said before. Moreover, when m equals 2, this gives you exactly the cross-section of the extremal Kerr horizon. And so when m is outside this open interval 0, 2, this is in fact the general non-trivial solution on a compact surface. So the only other case that I have left out is when this one-form dual to x is closed, but you can show that when this is closed, there are no solutions on a compact surface. So I'll spend a few slides on the proof of this. So first of all, we assumed that there is a Killing vector preserving the metric, but we also want to know that the Killing vector has to preserve the vector field x. So there's a local argument for this, and the result is that either the Killing vector preserves x, or the metric has constant curvature. And the second case simply means that you chose the wrong Killing vector. So if the metric has constant curvature, there are 3 Killing vectors, and there'll be another one which does commute with x. And the proof relies on the prolongation procedure, which was already considered in this context by Nurovsky and Randall. So you note that the Quasi-Einstein equation only prescribes the symmetrized derivative of x. So we introduce this function omega containing the anti-symmetric part of the derivatives. And then we get this prolonged equation, and now we can differentiate this again and commute some derivatives to get an expression for d omega, which will be a polynomial expression in x and omega with coefficients depending on the metric. And then we have closed our system, and then we can continue differentiating to get constraints. So the first constraint would be given by differentiating the expression for d omega. This was already done by Nurovsky and Randall. However, we will need also the second and third constraints, which you can get by further differentiating. And of course, you could go on and on and on, and the formulas will get more and more complicated. It turns out that 3 constraints is enough. So the idea is that these three constraints are expressions that are polynomial in x and omega, and they have coefficients that depend on the metric. So if there's a Killing vector, then these coefficients are invariant under the Killing vector. And so if these constraints are sufficiently independent, then it will follow that x and omega also are invariant under the Killing vector. And so you can start trying to solve these constraints and take resultants, and it follows that whenever dr is not 0, you indeed have independent constraints, and the conclusion follows. And then finally, to get to the result, you want to exclude the possibility that the curvature is constant on some open set, but not everywhere. And for this, you can use real analyticity of solutions to the Quasi-Einstein equation. So just like for the Einstein equation in Riemannian signature, where the arguments were worked out by de Turck and Kasdan, the Quasi-Einstein equations form an elliptic system, which means that in appropriate coordinates, solutions are real analytic. And so either the curvature is constant everywhere or k commutes with x. And in both cases, there is a killing vector commuting with x. So now we know this, we can move on to actually solving the equations. It turns out to be useful to introduce this vector field phi, defined as x over the norm squared of x, at least whenever x is not 0. And so you can start contracting the Quasi-Einstein equation with x and with the Hodge dual of x, and you get some equations that you can write in terms of phi, and you'll get the following two equations. So the one form dual to phi is closed, and the divergence of phi is -1 over m. So the first equation means that we can introduce a function f such that df is -m times phi. And then the second equation reads the Laplacian of f equals 1, which means that f is a Kähler potential for the metric. So if we pick a local complex coordinate z, then the metric can be written in this way, where f z bar means d by dz of d by dz bar of f. And also by inverting this relation between x and phi, we can write x in terms of this function f. So we have now essentially solved 2 of the 3 Quasi-Einstein equations, and the remaining one is the trace. And so you can plug in this ansatz, and you'll find that the trace reduces to a 4th order PDE for this function f. So up until this point, everything was still general. We can now use the fact that there's a killing vector. So if there's a killing vector, then we now know that k preserves x. Yes. As far as I know this, we don't know.
Any chance you can write it down?
It's very complicated. It does not fit on one line.
Well, except the message seems to be that this integral will have -1.
Perhaps, yes, but that doesn't mean that I can solve it.
The symbol is square root of the plus.
Yes.
And there's a non-linear. We have it.
Yes.
Jenny likes big complicated things.
So if there is a killing vector, then we know that it commutes with x. So in particular, it preserves phi, and this implies that k applied to f must be a constant. And moreover, we can assume that this constant is not 0, because if the constant is 0, then k will be orthogonal to x, which will imply that x is closed, and we're assuming x is not closed. So then we can rescale k such that this constant is 1. And now we introduce these nice coordinates, x and phi. So we choose our complex coordinate z such that the killing vector is the imaginary part of d by dz. And then we introduce x and phi in this way. So you can arrive at these coordinates by staring at the 4th order PDE, or simply by guessing and comparing to the extremal Kerr solution, which takes the simplest form in these coordinates. So in these coordinates, the volume form is dx wedge d phi. So x will be a moment map for the u1 action. And moreover, if you plug in these coordinates, then this PDE for f becomes an ODE, which is the following ODE for the function b, which is the norm squared of the killing vector. And this you can solve explicitly in terms of a hypergeometric function. And this leads to the local statement in the theorem. Now for the global statement, we use the following lemma. So if we have a metric that has a killing vector d by d phi, and this function b is the norm squared of the killing vector, then it extends to a smooth metric on the 2-sphere if and only if b has 2 simple zeros, b is positive between the zeros, and at these zeros x1 and x2 there's this condition b prime of x1 is minus b prime of x2, and moreover we have to periodically identify phi with the right period. So the fact that b has 2 zeros comes from the fact that any killing vector on the sphere has exactly 2 zeros. And then these other conditions come from imposing the absence of conical singularities at these zeros. And so we now take B to be the solution of this ODE, and we try to impose these conditions. And this gets a little bit messy because of the hypergeometric function involved. But you can use an integral representation of these hypergeometric function to solve these constraints. And this is how you find that this constant B has to be 0, which in fact implies that capital B is an even function of x. You also find that these zeros have to satisfy x1 equals minus x2. And so now there's one remaining constant C left to fix. And so you have to choose this constant C such that B has 2 simple zeros. And this will lead to this table that I had in the theorem. And this completes the proof. So I come now to the second part of my talk, how I specialize to this value of M related to the projective metrizability problem. So a projective structure is an equivalence class of torsion-free connections sharing the same unparameterized geodesics. And we can reformulate this condition algebraically by saying that 2 connections are projectively equivalent if and only if they're related in this way for some one form. And the projective structure is metrizable if it contains a Levi-Civita connection, and it's skew if there is a representative connection whose Ricci tensor is skew symmetric. And so these conditions have been considered before, and people have found obstructions in terms of projective differential invariance. For example, Bryant, Daneshky, and Eastwood found necessary and sufficient conditions for a 2-dimensional projective structure to be metrizable. And there's also been some work deriving necessary conditions for a projective structure to be skew. And the problem I'll be interested in is to classify projective structures that are both metrizable and skew. And the way we'll approach this problem is as follows. So we start with the Levi-Civita connection of some metric, and then we try to find this one form such that the corresponding projectively equivalent connection has skew Ricci tensor. So if we define X by some rescaling of this one form, and let G be some metric whose Levi-Civita connection is nabla, then this condition of skew Ricci becomes the following equation, which we recognize as the Quasi-Einstein equation, where M is 1 minus N, and this other constant lambda is 0. And so the first observation I would like to make is that globally, on a compact manifold, there are no interesting solutions to this problem, because this M and lambda fits into a range of M for which there are no solutions on a compact manifold if lambda is less than or equal to 0. So the 2-dimensional version of this theorem I had on one of my earlier slides, in higher dimensions, you can prove this because this is the range of M for which we know that there has to be a killing vector. And when M and lambda are both negative, sort of the Quasi-Einstein equation implies that the Ricci tensor is too negative definite to have such a killing vector. So every solution has to be trivial. So corollary is that if we have a skew and metrizable projective structure on a compact manifold, then in fact the metrizable and skew representatives are the same, and they're given by some Ricci flat Levi-Civita connection. So from now on, I'll be talking about the local problem, and I'll also reduce to 2 dimensions. So we take N to be 2, and the corresponding values of M and lambda are -1 and 0. And sort of the observation that will start all this off is that we can form this connection nabla hat. So this nabla hat is no longer projectively equivalent to nabla. In fact, it's not even torsion-free. But it turns out that we can choose these constants 1/2 and -1 in such a way that the Quasi-Einstein equations are equivalent to this connection nabla hat being flat. And so this observation will lead us to a lax pair for the Quasi-Einstein equation. So to do this, we'll choose some coordinates. So we'll pick a local complex coordinate z, and such that the metric and one from dual to x take this form, where p is some complex function and h is some real function. And then in these coordinates, we can represent this connection nabla hat as a matrix valued one form, and these are the relevant matrices. So they contain components of G and X. And so the observation is that the quasi-Einstein equations are equivalent to these two operators commuting. And in fact, we can turn this into a Lax pair with a spectral parameter lambda by exploiting a scaling symmetry of these quasi-Einstein equations in these coordinates. So if we scale z by epsilon and p by 1 over epsilon, and then p bar by 1 over epsilon and z bar by epsilon, then x is unchanged, so the quasi-Einstein equations are unchanged. But at the level of these operators, this is a non-trivial transformation, which allows us to introduce a spectral parameter. And then we get the following Lax pair. So the other thing I did here is I performed a gauge transformation to make the matrices traceless. This will be useful later on to recognize the gauge group. So L and M commute for all values of lambda if and only if the quasi-Einstein equations are satisfied. And now we can compare this to the anti-self-dual Yang-Mills equations. So these equations are Hodge f equals minus f, where f is the curvature of some connection A. And in this case, I'm taking the Hodge star with respect to this metric eta, which is a complex metric on C4. And so Z, Z bar, Z, Z tilde, W, and W tilde are complex coordinates. And the volume form is dz wedge dz tilde wedge d omega dw wedge dw tilde. And so the anti-self-dual Yang-Mills equations in these coordinates are particularly simple, and they admit a Lax pair of this form, where d here is the covariant derivative, so it's the exterior derivative plus a. And now we can try to match the quasi-Einstein equations to anti-self-dual Yang-Mills by comparing the Lax pair. So for example, from this minus lambda dw here, we would want this to be the w component of our connection, and we would want this to be the z component of our connection. And in this way, you can see that the quasi-Einstein equations are a reduction of the anti-self-dual Yang-Mills equations by two translations, d by dw and d by dw tilde. So this simply means that these functions in here do not depend on w and w tilde. And moreover, if we take Euclidean reality conditions, so we take a slice such that z tilde is z bar and w tilde is minus w bar, so that this metric eta becomes Riemannian, then in fact this connection takes values in the Lie algebra of SU2. So for example, this matrix here is going to be the z bar component of A, this is going to be the z component of A, and you can see that the z bar component is minus the adjoint of the z component. And similarly for AW and AW bar. So in fact, we obtain an SU2 connection. And
in terms of T and the H, is it a known integrable system? Or it's a new integrable system?
well, we haven't completely been able to solve it yet, but so
No.
so this becomes a special case of the Hitchin equations, which is what we talk about now. So if you do this in general, this reduction by two translations, with Euclidean anti-self-dual Yang-Mills, you'll get the Hitchin equations.
There will be a potential for this Sine-Gordon like equation.
I was going to say,
Yes.
the Sine-Gordon has something, but the Sine-Gordon has the block there diagonal, but the coefficients of lambda 1 over lambda are ordinarily off diagonal.
Well, Sine-Gordon is coming.
Oh, maybe it's this Sine-Gordon, sorry.
But
Maybe
it's not. It's becoming a bit stuck.
It will become one single equation, and maybe you can tell me what it is. I mean, we don't know.
Yeah, no, I think you need to mention.
I see. I see. Well, so in general, if we have the Euclidean anti-self-dual Yang-Mills equations reduced by two translations, we get the Hitchin equations. So this will allow us to associate a solution to the Hitchin equations to our problem. So let me briefly introduce the Hitchin equations. So the situation is, as I just mentioned, we have a connection A on some principal SU2 bundle over R4 with curvature F satisfying the anti-self-dual Yang-Mills equations. And this Hodge star is taken with respect to the standard Riemannian metric on R4. And we assume that the connection is invariant under two translations d by dx3 and d by dx4. And moreover, we will restrict our gauge transformations to those that preserve this form. So the gauge transformations are only allowed to depend on x1 and x2. Then we can take the first two components of the connection and turn them into a new connection A, which is now a connection on R2. And the remaining two components of the connection, we can take this complex linear combination and multiply by dz, where z is x1 plus I times x2. And then we call this phi, so this will be a 1-0 form with values in the complexified Lie algebra. And under this residual gauge transformation, it transforms in the adjoint representation. So now you can write down the anti-Self-Young-Mills equations in terms of this A and phi, and you'll get the following. So there's one equation involving the curvature of this new connection A, which is f is minus a bracket of phi with phi star, where phi star means take the adjoint of the matrix and replace dz by dz bar. And then the bracket means wedge the one forms and take the Lie bracket of the Lie algebra elements. And the second equation is that the 0-1 part of the covariant derivative of phi is 0. Equivalently, phi is a holomorphic section of this bundle with respect to the holomorphic structure induced by the connection. And so these equations are conformally invariant, and they can be studied on a compact Riemann surface. And this leads to a lot of interesting mathematics. But as I explained earlier, I will mostly be interested in the local problem. And another local observation is that the Hitchin equations imply that this connection A plus phi star is flat. And this will turn out to be exactly the connection that we started with. So I'll discuss a relevant example of a solution to the Hitchin equations that will be relevant to match our problem to Quasi-Einstein. So for this solution, we start with some metric G0, which is some conformal factor omega times dz bar on some Riemann surface M. And we write K for the canonical bundle. So then we take some square root of K and define V to be K to the 1/2, the square root plus the dual of the square root. And then the Chern connection of the metric will induce some connection on V, which gives V an SU2 structure. And then we take P to be the associated principal bundle with the associated connection. So this gives us A. And then phi we can view as a 1-0 form with values in the endomorphism bundle of V, such that these endomorphisms are traceless. And then phi will be given by the following, where this matrix refers to this decomposition of V. So this 1 here corresponds to the slot where we have a homomorphism from K to the 1/2 to K to the minus 1/2. And of course, we have to still tensor with K because phi is a 1-0 form. And because this bundle here is canonically isomorphic to K to the minus 1, there is a canonical section of this bundle, which I call 1. So if we so it's the connection on the holomorphic tangent bundle that in holomorphic trivializations, the 0-1 part will be 0, and moreover, it is compatible with the metric. So there's a formula which is essentially this form. So the Chern connection will be dz log omega squared times partial z of log omega squared times dz in a trivialization. And this induces the following connection on this bundle V. So if you pick a complex coordinate z, we can write everything down as just matrix values 1 forms, and we end up with this phi and this A. And now you can see explicitly that this phi is indeed holomorphic. And moreover, so there's still one Hitchin equation left, the one involving the curvature of this connection. And well, you can just calculate it now from using these coordinates, and the condition turns out to be equivalent to the metric that we started with, having constant Gaussian curvature equal to -4. Okay. So I'll now explain how to relate this example to the Quasi-Einstein equations. So by what I said before, we get a solution to the Hitchin equations associated to this Quasi-Einstein structure. And the corresponding A and phi are as follows, where we call that this P and H were components of the metric, and X satisfying Quasi-Einstein. And now you can see that this connection actually takes values in a U1 subalgebra of SU2. So this is a suggestion that maybe this connection is defined by some metric. And so maybe we can find a gauge transformation from this A and phi to the A and phi that we had here for some omega. And it turns out that you can. So you have to take omega to be mod p. And then, well, there's, of course, still the phase of p, which corresponds to the U1 gauge transformations preserving the form of this connection. And you have to choose this function alpha in such a way that this second condition holds. And moreover, the Quasi-Einstein equations imply that there always is such an alpha. So for every solution to the Quasi-Einstein equations, the corresponding solution to the Hitchin equations is gauge equivalent to the one defined by the metric mod p squared dz bar. And then a corollary is that this metric mod p squared dz bar must have constant curvature equal to -4. And we can write this metric invariantly in the following way. So a quarter of the norm of x squared times g. So this observation will fix mod p as a solution to the Liouville equation. But of course, to solve our original Quasi-Einstein equation, we still need to solve for alpha. And alpha will satisfy an equation coming from here and the condition that we want h to be real, because h was this conformal factor in the metric. So if you impose that d by dz of d by dz bar of h is real, you'll end up with a condition on alpha, which is the following. So yeah, I've chosen the complex coordinate here such that this constant curvature metric is in the upper half plane model. And you get the following equation for alpha. And so this is where we are a bit stuck, because you would expect this equation to be somehow integrable, as we got it from anti-self-dual Young-Mills. But we don't really know how to solve it.
So we got stuck here. We do not stop for the when you see on we don't this because it comes on solutions lacks the connection is already flat. It's an integrability condition on this integral. We ask Sokolov whether there is a classification of equations of the form Laplacian of alpha equals stuff which doesn't only depend on alpha but also on first derivatives. And he said that there isn't his equations of the time, but it's not one of those. We've been looking at it for a while, but we're stuck. It looks a bit like sine Gordon.
But for sine Gordon, you just have both top and bottom Gordon. But so it's only off diagonal. But so it looks like there's some scaling in this sine Gordon, where taking depth pi squared goes to 0. I mean, depth pi squared is forced to be holomorphic. Usually pi times, I mean, it'd be sort of 1 or something. Yeah, so it's some scaling of what cycle.
This one is
Probably, yeah. Sorry, but I can find my favorite sine Gordon instead.
yeah.
But depth pi would not be 0.
I see.
I mean, there's a generalized sine Gordon where depth pi function, but we scale it to be constant, cross pi z. Right Gordon structure, so it's constant, then it is completely greater sine Gordon. Well, yeah.
Yeah. So the problem is that if you write this a and phi in terms of mod p and alpha, then there will be no equation for alpha. The Hitchin equations will not imply any equation for alpha. This equation really comes as an integrability condition from the condition that h is real. And so, well, at least in general, we have now reduced these Quasi-Einstein equations to a single second-order PDE. And you can look at maybe some group invariant solutions to this PDE. And this leads to another 2-parameter family of explicit solutions that are different from the 2-parameter family I showed you at the beginning. But yeah, as for the general solution, we don't know. So now for the last part of my talk, I'll move on to Quasi-Einstein in higher dimensions, and with M related to this Einstein-Weyl equation. So I'll start with defining a Weyl structure, which is on a manifold M, which is a conformal class of metrics, together with a compatible connection D, which means that if you apply D to any metric in the conformal class, you'll get some one-form tensor, the metric you started with. And such a Weyl structure is said to satisfy the Einstein-Weyl condition if the symmetric part of the Ricci tensor of this connection D is proportional to the conformal class. So for example, you could take D to be the Levi-Civita connection of one of these metrics, and then the Einstein-Weyl condition is simply the Einstein equation for this representative metric. But this is more general, so D doesn't have to be the Levi-Civita connection of any of these metrics, and the Ricci tensor of D doesn't have to be symmetric, but this equation still makes sense. So we can view such a Weyl structure as being defined by a representative metric together with the corresponding one-form omega, with the understanding that if we rescale our metric by e to the u and we add du to our one-form, we get the same Weyl structure. So if we now fix some metric in the conformal class and again define x by some rescaling of this one-form, we can write down the Einstein-Weyl condition in this frame, and you'll end up with the following equation, which looks very much like Quasi-Einstein, where this m is 2 minus n. However, the difference is that here this function capital lambda doesn't have to be constant, and we would like it to be constant. And in fact, you have to allow this to be an arbitrary function in order for this equation to be conformally invariant. And well, in the compact setting, this equation has been studied, among others, by Paul Todd. And it turns out that there is a very useful frame. So we can always find a frame such that the vector field dual to this one form, which I'm suggestively calling K here, is divergence free. So you'll start in an arbitrary frame and you try to solve for a conformal transformation such that in your new frame you have this property, and you'll end up with some PDE on a compact manifold, and then Godichon showed that you can always solve this PDE. And so in this frame where K is divergence free, if we assume that the Einstein-Weyl condition holds, and if we assume that our manifold is compact, then in fact this divergence free vector field has to be killing. So what we can do here is we contract the equation with the covariant derivative of K, and so x is K here, so there will be a term that has the norm squared of the Lie derivative, and then using the fact that K is divergence free, you can show that all other terms integrate to 0. And then on the compact manifold, it shows that K has to be a killing vector. And so in this frame, the equation is much simpler because this term is just not there. But of course, what we're really interested in is solving the Quasi-Einstein equation. So what we want is to find a frame where this function lambda is a constant. And the strategy will be as follows. So we start in this Godichon frame where everything is simpler, and then we try to find a conformal transformation that will take us to the Quasi-Einstein frame. So we try to solve for this function u such that in this new frame, the capital lambda is a constant. And this will impose a PDE on u, and the PDE is the following, where here this little lambda is what we want to be capital lambda in the new frame. So this little lambda has to be a constant. And using very similar arguments as before, you can show that in fact K has to preserve this function u, this term is 0, because you can multiply the whole expression by the Lie derivative of u and integrate over the manifold, and so you get a term with the square of the Lie derivative, and using the fact that K is killing, and then you can show that all the other terms integrate to 0. So this is very nice because this means that in fact K is not just a killing vector in the Godichon frame, but it's also a killing vector in the Quasi-Einstein frame, because it will preserve this rescaled metric. And so what we get here is that, so moreover, this K will also commute with this one form. So we find that for this value of m, any solution to the Quasi-Einstein equation on a compact manifold has a killing vector, just like for a bunch of other values of m. And another consequence, as I explained before, is that this lambda has to be positive in order for the Ricci tensor to not be too negative definite. So a quick summary of what we have so far. To any solution to the Quasi-Einstein equations on a compact manifold with this special value of m is of the following form. So the constant lambda has to be positive, and it's of the following form. It's given by rescaling a solution of the Einstein-Wahl equation in the Godeschon frame, which is this equation, and the function doing the rescaling satisfies this PDE, and moreover it is invariant under K. So I'm going to now restrict to the three-dimensional case. In 3 dimensions, this equation can be completely solved locally. This was done by Paul Todd. And there are 4 types of solutions. First of all, there are constant curvature spaces, which corresponds to taking this K to be 0. Then there is the product metric on S2 times S1. There's the Berger sphere, which is another homogeneous solution. And then there is one more 4-parameter family of solutions, which contains a 3-parameter subfamily that is globally defined on the 3 sphere. So what we have to do now is we have to solve this PDE on these backgrounds, and this will give us a general solution to Quasi-Einstein. So I've only managed to solve this PDE in one of these cases, which is the case S2 times S1. So here we have just the product metric, and the killing vector is d by dt. And since we know that K has to preserve U, we know that U doesn't depend on T. So in fact, U is a function on the 2 sphere. And then capital lambda is 1 here.
So it looks close to Taub's equation.
Yes, well, it is one of these prescribed curvature problems.
But if it's Taub, then you don't expect locally, you don't expect
So the constants are exactly right here for this to be one of these prescribed curvature problems, which means that you can actually solve it. So this is the equation for the metric e to the u times the standard metric on the 2 sphere to have constant curvature 2 lambda. So this means that the general solution is given by conformal transformations of the sphere, which are going to preserve this constant curvature. And so this e to the u simply has to be the conformal factor associated to Möbius transformations. So the conformal transformations of the sphere. And this allows you to just write down the general solution to this equation on the 2 sphere. So this solution is interesting for at least 2 reasons. First of all, well, it's known that there are no Einstein metrics on S2 times S1, but this shows that there are quasi-Einstein metrics on S2 times S1. And second of all, when this is the general solution for which this one form x is closed but not exact. So it's not exact because it will have a bit of dt and it will have a bit of du, where t is the coordinate on S1, so dt is not exact. And so such solutions have been classified for positive m. The result is that x always has to be parallel. But now we have an example of a solution where m is negative, where x in fact is not parallel. So this shows that for negative m, the situation is more complicated. So this covers this case, and then of course there's 3 more cases. For example, for the constant curvature spaces, we'll have an equation Laplacian of u is some positive constant minus e to the u, so we can absorb this lambda by adding a constant to u. And you're trying to solve this equation on a compact positive Einstein manifold. And yeah, at this point, I don't even have an abstract argument that there exist solutions to these equations. I don't know. And also for the Berger sphere, again, this function lambda will be a constant. And in fact, you'll end up with an equation like this, but now this 2 is no longer a 2, but it will be some arbitrary constant less than 2. And so this equation loses its geometric meaning, and it's unclear how to solve it anymore. And then for this 3-parameter family on the 3 sphere, it gets even more complicated because then this capital lambda is not even constant anymore. So solving this, saying something about solution to this equation in the other cases is still work in progress. So to summarize, if you assume axisymmetry, the Quasi-Einstein equations on a surface are completely solvable, and you can find solutions on the two-sphere for any values of m and lambda that are allowed by the Gauss-Bonnet theorem. And in fact, when m is not in this open interval 0, 2, this is the general non-trivial solution on a compact surface. And then there's this special value of m for which the Quasi-Einstein equation describes Levi-Civita connections projectively equivalent to connections with a skew Ricci tensor. And although for this m there are no solutions on a compact manifold, locally the equation in 2 dimensions arises as a symmetry reduction of anti-self dual Yang-Mills. And this allowed us to find a corresponding solution to the Hitchin equations. And this reduces this reduces the problem to a single second-order PDE, so this equation for alpha that I had before. And then finally, there's another value of m, which is related to the Einstein-Wahl equation. So here, the equation describes special frames of Einstein-Wahl structures where this function capital lambda is a constant. And so assuming compactness in 3 dimensions, using this Gaudichon frame, you can reduce the problem to a single PDE of this form. So now, before I finish, I would like to mention that I'm still very much looking for other geometric contexts that could lead to Quasi-Einstein for different values of m. So if anyone has any ideas, I'd be very interested to hear about that. But with that, I reached the end of my talk. So thank you very much.
Questions? So the last point. Einstein-Wahl structures in dimension 3 are integral. So it's an integrable system. But this equation, not when you delta u equals constant minus e to the u, this u will be the constant. It's not integrable. How can it be that one is a reduction of u?
So here I'm not saying, this is just, I'm trying to write these Einstein-Wahl structures in a particular gauge, or I'm trying to find a particular representative metric in this conformal class. So I'm not saying anything about the reduction.
So there is no claim that this PD comes as a reduction of Einstein-Wahl?
No, no.
There is no such.
No. This is simply the PD that I have to solve if I want to find the representative metric in this conformal class that will satisfy my Quasi-Einstein equations.
So is the statement that Quasi-Einstein equations are a fixed metric?
Yes.
In the Einstein-Wahl conformal, but they'll be in the Einstein-Wahl conformal class.
Yes, that's right.
But you still need to do more. You need to find this u.
Yes, because the Quasi-Einstein equation is not conformally invariant, so you have to break this conformal invariance somehow, and this involves solving this equation. Tim?
Maybe this is not a very well posed question. So going back to the Hitchin, in relation to Hitchin's equations,
Yes.
the sort of point in the moduli space of solutions you get is a very distinguished one. Uniformizing. When you get the uniformization, the quadratic differential is 0. Is there some, presumably you would have said this is the case, change the parameters of the Quasi-Einstein equation, you can't get more of the moduli space, and if not, is it some way, is there something obvious that's missing from the Quasi-Einstein equation that means that you can't get more of the?
So there is only this Lux pair, and this flat connection really relies on this particular value of m. It doesn't work for any other m. So this is, I don't know how I could find other solutions in this moduli space. Everything has to come together exactly to